Nuclear process. Fusion. Fusion is a nuclear reaction between two or more atoms that are joined together to form one new type. A diagram explaining the nucleus force, with the positive charges plus the neutrons. High speeds overcome the EMF, which usually repels the nuclei. Fusion equation. You start with one proton and two neutrons, plus one proton and one neutron, which then is two protons and two neutrons, plus the remaining neutron and energy. So now you have the explanation of the process. Fusion starts with two smaller atoms. You also have the fusionable nucleus. When close, the strong force overpowers the EMF strong force, which sticks the nuclei together. The next step is the nucleus joining, which leads to energy. The stable nucleus is formed, requiring less energy. The leftover energy is then released. You then have the nucleus product. The end atom must be stable in order for fusion to occur. Fission. Fission is the action of dividing or splitting of the atom into two or more parts. Equation example. For example, you start with the neutron, and we'll use the element uranium. So uranium has an atomic mass of 235 and an atomic number of 92. Next, you need to add one neutron, so the atomic mass is now 236, which then is distributed into two elements and remaining neutrons. So explaining the process, fusion always starts with a large atom, so the neutron goes into the nucleus of the large atom. Now there is a nucleus where the strong force becomes distributed. So there is a battle between EMF and the strong force. The like charges repel, smaller nuclei form. Energy is then released because less is needed to bind nuclei. Also, the EMF splits nucleus, so the strong force is now strong enough. So you can have extra neutrons, and atoms can either be stable or unstable. So fusion versus fission. So for the natural occurrence of the process, fusion occurs in the stars. The most important one would be the sun. In fission, it doesn't normally occur in nature. For products of process, fusion has few radioactive particles and fission has many highly radioactive particles. For conditions, when looking at fission or fusion, it has high density, high temperature, and high temperature environment is required. When looking at fission, the critical mass of the substance and high speed. Neutrons are required. Energy requirement for fusion is high energy is required. The energy requirement for fission is little energy. And the energy released from fusion is 3 to 4 times greater than the energy released from fission. And the energy released from fission is about a million times greater than the energy released from chemical reactions. Continuing with fusion and fission. Nuclear weapons. Fission is a hydrogen bomb, and fission is a fission bomb, which can also be an atomic bomb. The energy production for fusion is experimental technology, and for fission, the energy production is used for nuclear power plants. The fuel released for fusion is hydrogen isotopes are the primary fuel, and for fission, the primary fuel is uranium. They both obey the law of conservation and also stop when the fuel runs out. Nuclear decay and half-life. Nuclear decay definition. A nucleus of an unstable atom that loses energy by emitting ionizing radiation. So there's 3 different types of decays. There's alpha, beta, and positron. Summary of what happens. Well, in alpha, 2 neutrons and 2 protons leave. In beta, 2 neutrons change to protons, and in positron, protons change to neutrons. The isotope symbol of what is emitted is listed. What happens to the number of protons for alpha? It loses 2 protons. For beta, it gains a proton, and for positron, it loses a proton. What happens to the number of neutrons? Alpha loses 2 neutrons, beta loses a neutron, and positron gains a neutron. What happens to the mass? For alpha it decreases, and for beta and positron they both stay the same. Why would the atom seem to undergo this decay? Because alpha decreased the mass. For beta, it increases protons and decreases neutrons, and for positron, it decreases the protons and increases neutrons. Half-life definition is the amount of time it takes for the half of the radioactives within an element to become stable. So let's say you have 12 unstable radioactive atoms that are blue. But one half-life is 2 days. So in 2 days, half of those blue radioactive atoms now turn gray. You continue until all the atoms are stable. So now 2 half-lives is 4 days. Within those 4 days, 9 of the radioactive atoms turned to gray, which means they are stable. Goes through the same process, so in 3 half-lives, there's 1 remaining radioactive atom. Now here, they are all gray, resulting in stable atoms. So it took 8 days, or 4 half-lives, for all atoms to become stable. And that is all about the nuclear process.